Welcome, this is Dr. Amanda Rockinson-Zapke. This tutorial will provide an introduction to statistics. We will specifically define the two branches of statistics, descriptive and inferential. We'll look at the factors that are needed for choosing a statistical method, and finally we'll define and look at the difference between parametric and nonparametric procedures. Let's get started. The field of statistics exists because it is usually impossible to collect data from all individuals of interest or from an entire population. Our only solution then is to collect data from subsets or a sample of individuals of interest or a sample from the population, because really our desire is to know more about the population. Now, whenever we collect data from a sample, there's two different types of statistics we can run. The first is descriptive statistics. Descriptive statistics are used to describe the sample or summarize information about them. Examples of descriptive statistics include mean, median, mode, and standard deviation. Then there are inferential statistics. Inferential statistics are used to make inferences or generalizations about the broader population based on the sample data. Examples of inferential statistics include t-tests, ANOVAs, and correlation analyses. Now, the type of descriptive statistic that is reported or the type of inferential method that we run depends on several factors, and we're going to talk about those next. But before we start talking about them, or as we begin to start talking about them, it's important to note that there are some differences of opinion and controversy about these factors and how they should inform the choice of statistical analysis. Our discussion here will draw primarily from Warner, and this is a really good text to reference in order to better understand both the concepts and the controversies that surround them. She talks about this information in depth, and we're only going to do a brief overview here. For many research situations, there's usually more than one reasonable and appropriate statistical analysis. So when selecting a statistical method, convention says that the following should be considered: research design, levels of measurement or the type of variable, and also assumption violation and normal distribution of the population. As I said, we're going to briefly discuss these different factors here. However, again, I encourage you to read texts such as Warner and Tabachnik and Fidel as they really discuss these factors more in depth. The first factor we're going to discuss here is research design, and here you can see quantitative research designs listed. We're going to talk about quantitative research designs as Campbell and Stanley and Crowl discuss them. The first type of research design we're going to look at are descriptive studies. The aim of descriptive studies is to understand what is in a specific situation with an identified population. For example, let's say an educational researcher wants to know what is the overall sense of community of online students. The researcher does not attempt to manipulate or exert control over the phenomenon being studied. Rather, he or she simply wants to observe and measure it as it occurs. The researcher does not seek to examine any cause and effect relationship between variables. Thus, there's no independent variable in a descriptive study, and there's no dependent variable. Descriptive studies are often used simply just to gain knowledge about an identified problem before more sophisticated research is done. Now, descriptive studies vary in rigor. Thus, if conducting a research study for, let's say, a thesis or a dissertation, it's usually important to know the university policy on the use of descriptive studies for this endeavor. But again, the aim of descriptive studies, and what's important to understand here, is that descriptive studies are used to understand what is within a specific situation and identified population. Next, we are going to discuss correlational research. Correlational research examines the extent to which two or more variables relate to one another. So, for example, a researcher doing a correlational study may ask or may desire to know if a relationship exists between online students' sense of community and their course grades. Or the researcher may also want to know how sense of community scores can predict course grades. As the example questions imply, correlational research designs include two types of studies: prediction studies and correlational studies. Prediction studies are focused on prediction, the ability of one variable or multiple variables to predict another variable, and correlational studies simply examine the relationship between variables. Researchers often choose to conduct correlational study as an exploratory research or beginning research to determine if more rigorous research is warranted. Some researchers even consider correlational research observational research, as the researcher really does not manipulate any of the variables. So based on the example questions we just looked at, this would mean that the researcher would only need to collect student sense of community scores and course grades to conduct his or her study. No manipulation obviously is needed. The researcher who chooses to conduct correlational research, again, is simply desiring to examine whether or not a relationship exists between or among variables. The researcher thus cannot make any statements about a cause and effect relationship because he or she does not know the direction of the cause and cannot guarantee that one variable is influencing another variable. This is oftentimes why you might have heard a statistician say correlation does not equal causation. Experimental research is needed to determine if a cause and effect relationship exists. So this brings us to group comparison studies. Now we're going to look at group comparison studies. We're going to start with the causal comparative study, which is actually a non-experimental design. A causal comparative study examines the possible cause and effect relationship between variables. It's an ex post facto study, which means that the phenomenon is studied after the fact. That is, after it occurs naturally in the environment or has already been manipulated. For example, a researcher may want to examine if males and females differ in their sense of community when taking an online course. It's impossible for the researcher to manipulate the independent variable of gender, therefore, the researcher would conduct a causal comparative study. So, like our descriptive studies, the researcher does not attempt to manipulate or exert control over the phenomenon being studied. However, unlike our descriptive study, the researcher does seek to examine the possible cause and effect relationship between the variables. Thus, there is an independent variable and a dependent variable. Now, I'll stop here and note that I said the word possible cause and effect. Due to the fact that there are extraneous or confounding variables not controlled for in this type of design, the results of the research can only suggest that one variable may cause another, and more rigorous experimental designs are needed to verify these results. So let's go ahead and talk about experimental design. Campbell and Stanley in 1963 purported that there are three experimental designs: pre-experimental, quasi-experimental, and true experimental. The characteristic or the distinguishing characteristic of all experimental designs is that the researcher manipulates the independent variable. Let's go ahead and start talking a little bit further about each of these types of designs, experimental designs. Let's start with the true experimental design. The purpose of a true experimental design is to examine the cause and effect relationship between variables. True experimental designs are often referred to as the gold standard in research practice due to their rigor and controls for threats to internal and external validity. Now, the best way to think about a true experimental design is to think about its three characteristics. First of all, there's manipulation. Remember, I just said that the characteristic of all experimental studies is manipulation. So the true experimental design is characterized by manipulation. This means that the researcher manipulates the independent variable or implements an intervention and observes the effect of that intervention on a dependent variable. The second characteristic is control. A control or comparison group is used, and this is any group that does not serve as the treatment group. So the researcher can compare the treatment group to the control group or comparison group. A great resource for learning more about comparison groups is CASD in 2003. So now we've talked about two characteristics of a true experimental design: manipulation and control. Let's move on to the third. The third is randomization. The third procedure required for conducting this design is randomization. Now that's not to be confused with random sampling. Randomization involves the assignment of participants to groups on a random basis. This means that every participant has an equal chance of being assigned to any group. let's say we have a control group and a treatment group. That means that every participant who agrees to be part of the study has the opportunity to be assigned to either the treatment group or the control group. Now, according to Campbell and Stanley, randomization allows for the researcher to assume group equivalence. However, it is important to note that researchers like Gogol and Borg suggest that group equivalence cannot be certain without that pretest. But then Campbell and Stanley say when you add a pretest, you actually add a threat to internal validity. So let's just say here, because we won't go into great detail about that, that randomization allows for the researcher to assume group equivalence. So now to review, the characteristics, or 3 characteristics of a true experimental design, include manipulation, control, and randomization. I'll also note here that also many researchers and research texts say that random sampling from the population is also needed for a true experimental design. But of the 3 characteristics that we just talked about, the element of randomization is really what distinguishes a true experimental design from a quasi-experimental design. Now let's talk a little bit about quasi-experimental designs. Quasi-experimental designs determine causality of an intervention or treatment with a target population very similar to the true experimental design. Quasi-experimental designs use both a control group and allow the researcher to manipulate the treatment, but they do not include random assignment of participants. So there's 2 primary characteristics of a quasi-experimental design: manipulation and control. Quasi-experimental designs use either an existing groups, such as classrooms of students, and assigns them to either a treatment or a control group. Oftentimes, too, quasi-experimental designs can use participants as their own controls, such as we see within group designs and time series designs. But let's look at the idea that in a quasi-experimental design that we use existing groups. Let's say a researcher conducting a quasi-experimental design wants to ask, what effect does participation in an online educational statistics course developed using a problem-based pedagogy have on online students' achievement as compared to when students participate in an online statistics course developed using a traditional pedagogy? And let's say here in this example that Mrs. Smith's class, which has already been formed, receives statistics lessons using the problem-based pedagogy, and Mr. Jones's class, which has again already been formed, receives lessons developed using the traditional pedagogy. Again, since a quasi-experimental design uses groups that have been previously formed, a researcher needs to ensure that the groups are relatively similar to one another. That is, in our example, Mrs. Smith's class and Mr. Jones's class are similar in terms of their previous achievement in statistics, as well as other variables that could affect the dependent variables, such as gender and ethnicity. So any extraneous variable needs to be identified and controlled for. Oftentimes the way this is done in quasi-experimental research is to use a pretest. So a pretest is done and is controlled for statistically by using analyses such as an ANCOVA or MANCOVA, which we'll discuss in depth in later tutorials. Last but not least is the pre-experimental design, and we're not going to spend a lot of time discussing this because Campbell and Stanley actually say these designs are of little value due to the severe threats to internal validity. So what's important to note here is that pre-experimental designs are usually completed to obtain preliminary research data to determine the effectiveness of an intervention or treatment, and these are distinguished from true experimental and pre-experimental designs because they oftentimes do not have a control group, or they don't include a pretest and have severe threats, as I said, to internal validity. So, as we're concluding our discussion on the different types of research design, what's really important to understand here is the reason and the purpose of each of these designs. As we're talking about research designs, I want to make a quick note here. Every research and statistical text talks about different designs in a different manner. The purpose of the designs do not change. However, sometimes they're classified in different ways or called by different names. Statistical texts such as Warner classify research designs as they're listed here: experimental, quasi-experimental, non-experimental, and other approaches such as case study, time series, qualitative methods, and instrument development. I will note that one distinction that Warner discusses more in depth is the difference between the within and between subjects design. Let's take a look and define each of these because they become very important in choosing statistical analyses. Let's start with between subject designs or between group designs. This means that every participant is tested under one and only one condition. For example, in a randomized experiment with a treatment condition and a control condition, each participant is tested either under the treatment condition or under the control condition. Another way to say this with a little bit different terminology is that a between groups design is an experimental design in which different participants are assigned to different conditions in the experiment. That is, individuals who comprise the control group are different people than those who comprise the experimental group. And so that's our between subject design or between group design. Now let's talk a little bit about the within subject design. Sometimes it's simply desirable to use an experimental design in which every participant is tested under all the conditions. And this is called a within subjects design, or sometimes the term that you'll hear used is repeated measures design or time series design. So in this design, every participant is tested under every condition. For example, let's say that we want to know about students' level of concentration in studying statistics. And we want to look at two different conditions, a quiet condition and a noisy condition. And so we take a group of participants and we test their level of participation first in a noisy condition, and then we put them in the same group in a quiet condition and we test their level of concentration again. This is an example of a within subjects design. Now, Campbell and Stanley discuss within and between subject designs under what they term quasi-experimental designs. Understanding the difference is important, as I said, because there are different analyses used for within group designs and different analyses used for between group designs. So, it's important to know the different classifications within your field, but here the important thing to understand, as I said when we were discussing the previous slide, is the purpose of the design or the purpose of the design, because ultimately the purpose of the design will help you choose the appropriate statistical method. Let's take a look at an example of this. Now, the type of research design does not determine the choice of statistical analysis, but it can guide it, as the purpose of the design and analysis should align. Let's first look at between group experiments. Because between group experiments often involve comparison of means for quantitative variables across groups, independent t-tests and between group ANOVAs are often applied to examine this type of experimental data. Whereas a dependent t-test or within group ANOVA would not be appropriate. This would be more appropriate for a within group experiment that involves the comparison of means for quantitative variables across one group. And then sometimes a researcher simply wants to conduct a non-experimental design, such as a correlational study. And this, remember, involves measuring quantitative variables and examining the relationship between them. And so oftentimes an analysis that is aimed at looking at the relationship between variables is Pearson's R or Spearman-Rowe. So in these situations, in these non-experimental situations, the non-experimental data is examined using a correlational analysis. We'll talk about each of these different types of analyses in more depth in future tutorials, but here it's simply important for you to understand how the purpose of the research design informs and guides the choice of the statistical analysis. Now, while the research design guides the choice of the analysis, the choice of the actual statistic is based upon the type of variable that's used, either quantitative or qualitative, or how the variable's measured, the level of measurement. We can first discuss variables as they're discussed in many statistical texts, and that is as they're measured on one of 4 levels of measurement. And these were first described by Stephen in 1946. The 4 levels of measurement are nominal, ordinal, interval, or ratio. Nominal are categorical variables, that is, variables that can be put into categories such as religion or gender. Ordinal variables are categorical and ranked ordered variables, so they can be put into categories and then ranked, such as socioeconomic status, that can be described as low, moderate, or high. And finally, there are interval and ratio variables, which are measured variables. Interval variables do not have an absolute zero, whereas ratio variables do. We can also distinguish different types of variables, or distinguish between 2 major types of variables, and that's qualitative variables and quantitative variables. Qualitative variables are non-numeric and categorical variables, often described with words, and quantitative variables are variables that are measured numerically. Now, for the purpose of this tutorial, we're not going to discuss these different types of variables in depth. For a more in-depth discussion, I encourage you to review the variable tutorial part 1. Now, the type of variable that you have in a research study, or the variable's level of measurement, influences the type of graph that's used and the choice of descriptive statistics reported. Here you can see an example. Nominal variables, or qualitative variables, categorical variables, are often reported and described using frequency charts, bar charts, numbers, percentages, and modes, whereas quantitative variables are described, and these quantitative variables are more like your interval and ratio level variables, as well as your ordinal variables, are described in frequency tables, histograms, described using mean and median, standard deviation, the minimum, and the maximum. The level of measurement, or type of variable, as you can see here, also determines the choice of the inferential statistic completed, whether or not a nonparametric or parametric analysis is used. Here you'll see that nominal and ordinal levels of measurement can only be analyzed using nonparametric analyses. Interval and ratio levels of measurement, which are both quantitative, can be analyzed using parametric analyses. I will make note of one exception here, especially in educational research. Oftentimes, Likert type scale data is considered ordinal data. If we really think about it, it is ordinal data. However, it's treated like ratio interval data in educational statistics, and so therefore it's analyzed like interval and ratio level data. And so for Likert type scale data on surveys and different things that, especially validated surveys, that we use in educational research, those can be analyzed using parametric statistics. But that's just a small aside. The point here is that the level of measurement or type of variable determines the choice of either a non-parametric or parametric analysis. Now, parametric and non-parametric are 2 broad classifications of statistical procedures. It's generally easier simply to list examples of each type, parametric and non-parametric, rather than actually defining the terms, and we'll talk about why that is in a moment. Here I want you to take a look at the list of parametric techniques and then their alternative non-parametric techniques. Examples of parametric techniques include the independent samples t-test, the one-way ANOVA, the repeated measures ANOVA, whereas non-parametric techniques include the chi-square, the Kruskal-Wallis test, and the Mann-Whitney U-test. As I said, it is generally easier to list examples of types of procedures, parametric versus non-parametric, rather than define them. In fact, the handbook for nonparametric statistics from 1962, and that I know that's quite a few years ago, but this still holds true today, says this: a precise and universally accepted definition of a nonparametric is presently not available. The viewpoint adopted in this handbook is that a statistical procedure is of nonparametric type if it has properties which are satisfied to a reasonable approximation when some assumptions that are at least of moderately general nature hold. So, as you can tell, this definition is not really in the least bit helpful, but it does underscore the fact that it is sometimes difficult to define the term parametric and nonparametric. So for our practical purposes, we are going to say that nonparametric statistical procedures rely on no or few assumptions about the shape or parameter of a population distribution from which the sample is drawn. So then alternatively, we can say a parametric technique makes a number of assumptions about the population from which the sample is drawn. For example, it has the sample has normally distributed scores, and it also makes assumptions about the nature of the data, that it's measured at an interval or ratio level. So, what does this mean for us? Well, for a nonparametric, you conduct a nonparametric statistic if you have nominal or ordinal data. But when working with ratio or interval level data, as we've already said, you plan to use a parametric analysis. However, if the data you collect, even if it's when it's at ratio or interval level, has majorly violated assumptions, then it is more appropriate to use the nonparametric alternative. So this brings us to our third factor for choosing a statistical procedure, and that is assumption violation. Parametric procedures are based on a set of assumptions, such as the distribution of the underlying population from which the sample is taken is normally distributed. There'll be no extreme outliers, and the variance of scores are approximately equal across populations that correspond to the groups being studied, or homogeneity of variance. Whereas our nonparametric tests really do not rely on these assumptions about the shape and parameters of the underlying population distribution. So, for each parametric analysis, there is a specific list of assumptions that need to be met. So when you collect your data that's at interval or ratio level, you do assumption testing. So it's important for you to understand what the assumptions are for each parametric analysis and how they can be tested. Because if data deviates strongly from these assumptions, a parametric procedure may not be the best choice. And in fact, the non-parametric procedure may be the better choice. Because if you continue with the parametric procedure, with major violations of assumptions, what could happen is you could make wrong conclusions. Now, Warner, Tabachnik, and Fidel, and other statistical resources talk about that some minor violations of assumptions are okay, and they talk about when that is. For example, the parametric assumption of normality is particularly worrisome if you have a small sample size, let's say under 30. However, if you have a larger sample size, it may not be as worrisome, and therefore you may be able to continue with the parametric analysis. As you get into looking at individual procedures, it's important to consult statistical texts about this. But the important thing to remember here is that when you collect interval or ratio level data and you find that there are violations and assumptions, the parametric analysis may not be the best choice, and a non-parametric analysis may be a better option. So if parametric procedures have all these rules and regulations, and you have to meet all these assumptions, why not simply just do a non-parametric analyses or non-parametric procedure? Well, although non-parametric procedures have very desirable properties, such as making fewer assumptions about the distribution of measurement in the population from which that we draw the sample, there are some drawbacks, and there are two major drawbacks. The first is that nonparametric analyses or procedures generally have less statistical power than their alternative parametric procedures. This is especially when the data is not approximately normal. And less power means that there is a smaller probability that the procedure will tell us that the variables under study are associated or different. There's less of a chance that we'll find statistical significance. In order for a non-parametric analysis to be as strong as or have as much power as a parametric analysis, oftentimes it requires a large sample size. However, one of the nice things about the non-parametric analyses is that we can do non-parametric analyses with smaller sample sizes, but again, we just have less power. The second drawback associated with non-parametric procedures is that their results are often less easy to interpret and make sense of as the results of the parametric analyses. And this is because many of the non-parametric analyses or procedures use ranking of value in the analysis rather than the actual raw data. So, even though it may seem that a non-parametric analysis is preferable because you don't have to meet all the assumptions, the reality is they are less powerful and oftentimes more difficult to interpret. So if given the option, the parametric option is the better option. Now we've identified 3 factors for choosing a statistical method. Sometimes the easiest way to look at these 3 factors is to put them in question form. When you conduct a study, you can ask the following questions. The first question has to do with the type of variable or the level of measurements. When you conduct a study, you can ask, what level of measurement are the variables in my study? In an experimental study or causal comparative study, group comparison studies, as Campbell and Stanley categorized them, the dependent variable is really what we're concerned about here. In a correlational study, whether it be correlational focused on relationships or predictive, what we're concerned about is all of the variables, but mainly in a predictive study, we're concerned about that criterion variable. Now, once we've identified what level of measurement the dependent variable, the variables of interest, or the criterion variable is, we can make a choice about whether or not to conduct a parametric or non-parametric analysis. If our variables are, remember, nominal or ordinal, then a non-parametric analysis is going to be the best choice. If our data is either ratio or interval, then a parametric analysis may be the best choice. However, if the variables are measured at the interval and ratio level, remember the second factor for choosing a statistical method was assumption violation. So we ask, are the assumptions for the parametric analysis that we chose reasonably met? If they are, we can continue with the parametric analysis. If they're not, we may want to consider the non-parametric analysis. Now we consider research design. Research design can be very helpful in guiding us to a specific statistical approach. The first question that we want to consider in terms of research design is the design concerned with within-group or between-group comparisons? If it's a within-group comparison, then we're going to do a within-group analysis. If it's between-group, we're going to do between-group. And the final question about design that we're going to ask that's going to lead us to a more specific analysis is the design experimental or non-experimental in nature? If it's non-experimental, is it concerned with either differences or is it concerned with relationships? Because if you remember when we talked about research design, if it's concerned with differences, we may consider something such as a t-test or ANOVA, whereas if it's concerned with relationship, the relationship between variables, a relational or correlational analysis may be more appropriate, such as a Pearson's R. And then finally, how many groups are we looking to study? 1, 2, 3, 4, 5. Now that we've talked about the factors and we've talked about the questions that you can ask, let's go ahead and practically apply this. Let's say that a researcher is interested to see if there is a difference in college students' course points based on whether they participate in an online statistics course as opposed to a residential statistics course. Now here we can see that our independent variable is the type of course, the online or the residential, whereas the dependent variable is course points. So remember, the first question we're going to ask is what levels of measurement are our variables under study? Our independent variable is categorical or nominal. However, our dependent variable is measured at the ratio level, and that's really what we're concerned about. So since our variable is measured at the ratio level, the next question would be, are the assumptions of the parametric analyses reasonably met? Because remember, if we're dealing with ratio or interval variables, we're gonna consider a parametric analysis an appropriate analysis. Let's say for the sake of this study that our assumptions are met, so we can continue with a parametric analysis. So the next question we're going to ask is about research design. The question is the design concerned with within group comparison or between group comparison? So in this study, are we taking a group of students and are we putting them in an online course and then a residential course and measuring their course points both times, or do we have two separate groups that we're comparing? Well, if we look at the study, it says that you're looking at the course points based on whether students participate in an online course versus a residential. So this really implies that there are two separate groups. So we're going to do a between group comparison. Finally, we're going to ask, is the design experimental or non-experimental? Let's say that in this case the researcher actually assigned the participants to treatment, either residential or online, and therefore it's experimental, therefore it's concerned with the differences between the two groups. So we're concerned with differences, so that rules out our correlational analyses such as a Pearson's R. So the next question we're going to ask is, how many groups are they? Well, we have one independent variable with two groups here, the online and the residential. So now we have all of this information. We know that we're going to do a parametric analysis. We're going to then use one of Warner's decision trees to help us identify the specific statistical method that we're going to use. So here we see one of the decision trees that Warner often uses for hypotheses of difference for a parametric analysis. So we determined, remember in our example, that we were going to use a parametric analysis. We determined that it was a between group study that was looking at two groups, and we determined that we had two groups. We were looking at the difference between online and residential. So if we follow this down, we go parametric between two groups, we find that the analysis or the appropriate analysis is probably the independent samples t-test. Now, as you can remember, and as I said before, sometimes it's not quite so simple. This is a simple scenario that we walked through. Sometimes it's not quite so simple. And sometimes there are multiple analyses or different analyses that you could use. One example here could be that you could use an independent samples t-test, but you could also use a one-way ANOVA. And when we talk a little bit more about these different analyses, we'll talk a little bit about when one may be more appropriate than another. However, this helps you see how you can use the factors for choosing statistical analyses. And as I said, we'll talk more in depth later on about choosing specific statistical analysis. At this point, probably what's most important for you to know and understand is the difference between parametric and nonparametric analyses and the factors that go into choosing a parametric versus a nonparametric, and other considerations such as research design that will help you later choose a specific statistical analysis. This then brings us to the end of the introduction tutorial for statistics. At this point, you should understand that there are two types of statistics: descriptive and inferential and be able to define those. Be able to identify the 3 factors for choosing a statistical method and how they inform the choice. And then finally, you should understand the difference between parametric and non-parametric procedures and when one is more appropriate to use than the other.